Hi, I'm Chris Delion for Hobby Game Dev. In this latest video is going to be a short tutorial or walkthrough of doing some of the warm-up exercises for Brick Break, one of the games that are included in Code Pack 1 from the Code Pack bundle. The Code Packs are available from GameCodePacks.com at this time, and the prices arrangements might change, but currently I'm offering a short promotion where if you sign up by a certain time for my mailing list, you'll get a free copy of the Code Pack sample, which is all of the source code we'll be looking at today, and the walkthrough we're going to be doing together. And again, if you've never used processing before, you can get that for free from processing.org. In the download section, it's available for Mac, Windows, and Linux, 64 and 32-bit. So I've downloaded here in advance the Processing 2.1. I'm going to go ahead and unzip that. As well as the CodePack sample is the one which is included for that. And you'll see that when I unzip the zip file, that's all I needed to do. The program is right there ready to run. There's no installer configuration necessary. And once it's been run, it'll actually set us up with a directory. In my case, on a Mac machine, in Documents, I'll have a processing folder with some example sketches in it. Or if you're in Windows, it'll probably be under My Documents. And what I'm going to do to sort of install the code packs that we're going to start from as a source code, I'm just going to drag and drop this code sample here into the processing directory. Again, sort of in My Documents, depending on your operating system. And after doing that, I'm going to restart processing, because what that's going to do is it's going to put it into my listing of files that we can use. Now when I go to open, it's automatically included, CodePack sample. There you can see the common bonus, which is the source files that are free for all of the code packs, which include some lab example code, platformer source code, and some various tiny isolated examples, as well as sample Brick Break, which is what we're going to be looking at today for this walkthrough. Now additionally, I'm going to, let's increase my font size a little bit. Processing preferences, font sizes make it easier to follow. Let's say 24 instead of 12. Perfect. Okay, this will make it easier to see the code I'm typing on the screen. I know some of you don't want a full screen or run 720. And next, let's close down my browser. And now when I say the warm-up exercises, what I'm referring to is that in the code packs, it comes with a PDF file. So the bundles one is huge, 144 pages at the time of this writing. Might be longer after future updates. But it's got exercises included. And for the sample one, just the one for Brick Breaker code. Let me scroll down to where the warm-up exercises begin. You'll see there's some video links there for if you've never programmed before, in which I'll kind of walk you through the basics. There we go, Brick Break section of the PDF. Now first off, let's look at what the program currently does before we start walking through the warm-up exercises. Okay, put this over here. I'm going to keep, let's see, download directory don't need. I'm going to hang on to this folder though, it's going to be handy in a second. So this is the Brick Break code as it's provided sort of right out of the package, right out of the zip file. You'll see we have an element of ball control. We're going to touch the ball to the edge of the paddle. It takes an angle based on the distance from the center. It's a classic feature of these style of games. When I miss the ball, it resets the ball. And the ball bounces off bricks in an okay manner. It'll occasionally behave in slightly different ways than we'd expect. We actually addressed that in one of the later exercises included with the PDF that comes with the code pack. Sorry, I'm clearly trying to do too many things at once here. Okay, so that's the current state of it. And you'll see that it's lacking a lot of features that you'd expect a game to have, like scores or lives or different kind of levels. Those are the types of things we're going to address in the exercises. So without further ado, let's start looking at the warm-up exercises we've got. So first of all, for warm-up exercise number 1, code organization in multiple files. Currently, all of the code in the example exists in the same PDE source file, divided up into multiple files, each containing only the code and variables for the paddle, ball, or bricks respectively. For functions or variables that relate to multiple objects, collisions for example, feel free to keep it in the main file, or in the source file for either of the objects involved in the collision. And there's some details there, but I don't think we don't need to read those right now, because I'm about to show you what to do. Now, if you followed along the earlier videos I linked to in the PDF about sort of introduction to programming and processing, you'd know that to create a new file in processing is really the same as creating a new tab. I just go to this down arrow, I click on New Tab, and I can name it whatever I'd like. And so we want a different one for paddle, ball, and bricks, respectively. So let's create a new one called paddle. I'm going to create a new one. You'll see down here it asks for the name. Bricks, paddle, bricks, and ball. And these aren't the same as classes, which is something we're going to might move towards later in a future exercise. These are just creating separate files, which when I save my sketch, you'll see that here in my sample code for Brickbreaker, it's now created the separate PDE files for each of these tabs. They're currently just blank though. What we're going to do for this exercise, we're going to migrate the code that relates to each of these different parts of the game into the separate files. So, okay, ball values, as the comment says. Comment, of course, being any line of code that is ignored by the compiler, because in this case it starts with a //. I'm going to move those ball values over into the ball file. Do the same thing here for paddle values. Move those over into the paddle tab. Brick values, let's go ahead and get those over there too. I'm just cutting and pasting. That's, of course, Command X on Mac or Control X on Windows, and then Command V or Control V to put the text back down. So now we've got, in the ball file, we have the ball values, bricks has the brick values, paddle has the paddle values. So I want to point out there, I just clicked Command S to save, Control S, of course, in Windows. And one of the nice things about processing is it actually saves the whole project. So now all these files are updated to the latest form. And so that accounted for our variables, but we want to put not just the variables, but also the functions that correspond to the ball, paddle, and bricks into their corresponding files. And so we see a function here like reset bricks in setup. So in case you're new to processing, setup gets called once when the program starts, and draw gets called every single frame of the program. That's pretty typical for a game to be written on a per cycle basis like this. It's one function for initialization, one that's kind of your main or your core loop, within which you update any sort of logic, you draw things to the screen. But here we see, for example, reset bricks, parentheses, semicolon. It's calling the function reset bricks, but it's calling it, not defining it. We want to leave the call here in void setup because it has to happen when the program's starting. And let's instead move the definition of the function. We can tell its definition because it begins with the void or the return type of none here. And what reset bricks does, it loops through all the bricks, rows and columns, sets them to 1, so the game begins with a brick in every position. We're going to cut that. Actually, I'm going to uncut that because I'm just holding down Shift and using the down arrow to select multiple lines. I'm going to select reset bricks as well as draw bricks. I'm going to cut both of those functions and paste them here into our bricks file. So now draw bricks and reset bricks come after the variables in our bricks file. Same thing for the functions below that, back in our main source file. Ball reset, ball movement, ball hit check. Like I said in the warm-up, or the exercise, even though this involves more than one object in the world, we can put in any one of the files that it kind of matches up to, and this one, of course, is pretty central to the ball. And ball draw, ball move and draw. I'm going to cut all those functions. Again, I was just shifting down to select multiple lines at a time. Command X to cut. All those were ball functions. I'm going to paste those into the ball file. I scroll up and you'll see I have all those functions that started with the word ball are now in the ball file. Do the same thing here for paddle. Shift and down, all these functions that start with paddle. I'm going to paste those into the paddle file right below the variables. And now this is the exact same program we had a moment ago before we did this warm-up exercise. It runs exactly the same. It does exactly the same thing. The behaviors are no different. What is different, though, is that our code is more organized now, so that our main source file is actually really short. All it has is our screen definition, width and height of our window we want to use, a setup function setting the resolution, reset bricks and reset the ball, changing the function for draw so there's no outlines, and then our draw function, which is going to white out the screen or make it a certain shade of dark blue, followed by drawing the bricks, moving the paddle, and moving the ball, drawing each one as it moves it. And that gives us a very good high-level way to look at our program, beyond which, when future exercises have us looking at particular parts of the program, like the ball or the bricks or the paddle, we can go specifically into those files, and we know that our variables and our functions we're going to need to update for those exercises are going to be there organized for us. And this is a normal part of trying to expand a program from beyond the initial hacky prototype into something that you're prepared to really grow and begin to do more sophisticated things with. So that's the end of 2.1.1. Let's look then at keep and display score. So the project in its current state doesn't yet keep score. We can later make score more involved with varying brick types or power-ups with bonuses, but for now earning 100 points per brick removed will be a good starting point. Until we implement lives, we'll just reset the score each time the ball resets. Sounds reasonable enough. Okay, well, to do that, you might think at first, because we have this grid of bricks we already have that we're calculating, we could somehow multiply the number of bricks that are removed by 100 or something. It's even easier than that. All we need is a score value, an integer, because we just want discrete values like 1, 2, or 3, or -5. We don't need 2.6 or 9.3 or whatever. So we're going to use a score. And it said whenever the ball resets, we're going to reset the score for now. So I'm going to go here into ball reset. And there I'm going to say score equals 0. So when the ball gets reset, score will be zeroed out. And 100 points per brick removed. So let's look into our bricks file. And does any of this deal with the brick removal? It actually doesn't. If we think back to the earlier point I made about collision between two objects could show up in either file, remember it's a ball to brick collision. We have this function in the ball file called ball hit check. That's actually where we want to look in order to see, okay, here we go. If it equals 1, the brick that corresponds to where the ball is, then it sets it to 0. In other words, if we look at the comments, if there's a brick still there, then clear the brick. That's the right moment for us to add 100 points. Remember, this plus equals is a shorthand for saying score equals score plus 100, because equal signs in programming don't work the same way they do in mathematics. Here, it's not an equality. It's saying take the value on the right. So we're substituting the value score was, we're adding 100 to it, and then assign it into the value on the left. And so it's going to make score that number. And plus equals is just the shorthand for saying make this number 100 more than it was. So because this only happens when there's currently still a brick there, and the very moment that it removes that brick, we're in good shape. That's going to add 100 points every time. Now there's still a problem of we're not yet displaying the score on the screen. And so to do that, let's add a text call into draw. Let's do it at the end of draw. I mean, because if we did it like, say, first line, we'd actually be overriding it or overlapping it when we cleared the screen from the previous draw buffer. Instead, we're going to put it at the end because user interface elements like text, you'd expect to kind of overlap anything else. You don't want the ball to go over your score number and so on. And here we just have the value we want to display in text, and then the x and the y coordinate. I believe that's the order, and if it's not, we're going to find out pretty quickly. I'm going to press play. There, you can see there's a 0 up there. Now it's 100, 300, and each time I knock another brick out, I'm getting another 100 points. And because we put score equals 0 in the ball reset function, if I miss it, the score zeroes back out each time I miss the ball, and it goes right back to accumulating by 100 points each time. Okay, that's the end of the second exercise. And again, if you didn't have me here in the video to help you out, that's why I got the details in the PDF, so you've got some additional information to work from, some clues about what to look up in the processing reference, which is excellent, by the way. The resources at processing.org are amazing for answering little questions you get about how to display text and so on. Okay, next exercise, exercise 3 for Brick Break, is life limit then reset. Having score reset each time the ball is lost seems a bit harsh. Typically, a game provides at least a few chances before clearing score. Additionally, as long as we're only going to zero the score once every few misses, it makes sense to reset all bricks at that time too, as a signal of a full reset. Introduce a lives remaining variable, displayed during play, which decreases whenever the player misses the ball. When that lives number drops below 0, reset the score and all bricks. So fundamentally, this actually has a lot of similarities to the score we just implemented. Except instead of having an integer we're going to add 100 to each time on a certain occasion, we're going to have an integer of lives that we're going to subtract 1 from on certain occasions. And when it falls below 0, that's where we're going to handle certain reset functionality. Let's do this one thing at a time. So int lives, we know we're going to need lives. And let's see, how many lives do we want to have? Does we define a number up here? Let's say 3. In fact, I want to define this in a single place, so I'm going to say final int lives at start equals 3. And we're going to reset this in certain situations, but first of all, let's just set it to 3 at the start. Now, why did I do a final int with all capitals? It's a tradition or convention in programming that if you have a number that can't be changed, and final means it can't be changed, then you use kind of all capitals and underscores. It dates back to the days of C. But this is a way that I can then elsewhere in the code, when I want to reset the game, say lives equals lives at start, and have a single place and semantically encode where I can change that number, know exactly what the meaning is of the number I'm changing, and rely on that number not changing throughout the program. Okay, so we have a lives value, but now we need to make it decrease in certain situations. And that situation, of course, is when the ball escapes down the bottom. And if I scroll along there's ball paddle, ball movement is probably my suspicion. Here in the ball movement function, yes, so if the ball's Y position goes below the screen height, so it's off the bottom edge, then we're going to reset the ball. Well, we could put the lives decrement here, right here, or we could put it inside ball reset. I'd say for now, let's put it right here. Seems like it's a good place to sit in for now. That's going to decrease the number of lives that we have. Now, before we worry about making any of the rest of this stuff work, let's just get that much. Let's just verify that this works so far by displaying the lives number on the screen. We'll do it just like we displayed the score number. I'm going to say text, lives. I'm going to say screen width minus, let's try 15, see if the number is still visible. And we should, in the top right of the screen, yeah, you can see the number 3 there. That's the number of lives that we have. And if I miss the ball, it goes down to 2. And if I miss the ball again, down to 1. And I can keep doing it, and it's going to go into negatives because we're not yet checking to see if it goes below 0. Which, of course, leads to the next thing we need to do, which is to say that when we reset that ball, let's check out the ball reset function. That's where we're currently zeroing out the score. But we only want to zero out the score if lives falls below 0. See? So if lives is less than 0, then we're going to say score equals 0 to zero out the score. While we're at it, let's bump lives back up to the initial value that we want them to start with for the game, which remember is why we set up this constant lives at start. I just double click on the word to select it, copy, equals lives at start. So now when the ball's being reset, if the lives are at that point below 0, then we're going to zero out the score and reset the lives. And I think it also said we want to reset the bricks as a signal of the fact the game is receiving a full reset. Well, how would we reset the bricks? Like go right over to the brick tabs, and the first thing that hops into my face is a function written here called reset bricks. Well, even if we didn't know how it worked, and we should look at how it works, but even if we didn't know how it works, I can copy that function, slap it in here, so that when lives is below 0, it's going to zero score, bump my lives back to the starting value, as well as reset the total brick grid. Let's see if this works. So, playing the game, starting with 3 lives, you can see the number in the top right. And this time when I lost the ball, I have 2 lives, and you see score didn't reset, because score is 400, 500, I miss it. Down to 1 life left, 700, still didn't reset score, down to 0 lives, and now, when I miss that last ball, then it resets my lives back to 3, and it zeroed my score back out. This is gradually coming together as a more fleshed out game, right? I mean, these weren't even very hard to do, but these make the difference between something that's kind of not ready for players and something that gives them some practice space, some clarity, some sort of investment into making progress in it, and so on. So that's the end of the third exercise for Brick Breaker. And of course, if you're using CodePak Bundle, the full version, your first chapter section is going to be different because there's 5 other total games in the CodePak Bundle. But I'm sort of using the numbers here from the trial pack, so bear with me. Now let's see. 2-1-4. Click to serve the ball from the paddle each round. With lives in the game, it's now a problem that the first shot of each round is easily missed. To be played in its current form, the player has to be expecting the ball drop after each loss, rushing right to where the shot will be. Instead, let's start each round with the ball just above the paddle and a bit to the side, so it shoots upward at an angle upon the player's next click. Alright, so this is slightly more advanced than the previous example, but not too much more so. Because instead of having an integer, like we did for score or lives, we're going to have a boolean to keep track of, is the ball currently stuck to the paddle? Boolean, ball is, well, let me start with is ball held? Starting, so first of all, whenever you see this tradition in naming files, or naming variables rather, where the first word is lowercase and all consecutive ones are capitalized, that's called camel case. It's very common in programming because you can't have spaces in variable names. And you'll see that the lowercase is at the start is often used for booleans because that tells us elsewhere in the code this is a true-false value, not a 1, 2, 3, 4, 5 or 2.6. Remember, floats give us the decimal point, integers don't. Boolean is simply true or false. So is ball held? Let's go and say in ball reset, we're going to set is ball held to true. So we have a flag. We're not using it for anything yet, but we have a flag now of whether or not the ball is currently held. and if it's held, we're saying true. And what we're going to do is we want to check and see elsewhere in the code if the ball is being held to not let it move, and instead keep it next to the paddle until the player clicks. Let's look in ball movement. So here's where it's applying the ball's current speed and doing the wall checks and so on. We're going to short circuit this by writing an if at the top of the function. If is ball held, and notice, for example, we could say equals true, but that's sort of what's implied in using a Boolean variable. So if is held ball is equal to true, two equal signs there because it was an equality check, not an assignment, then we want to do two things. First of all, we want to update the ball's position to the paddle nearly, but offset. So let's look at the paddle's coordinates. The paddle has a paddle x value and a paddle y constant because its height on the screen doesn't change. So if ball is being held, we want to update its current position to the paddle's position, ball y. And again, you gotta look out because this one is a constant, all capitals underscore, that helps us make sure we don't get these two numbers mixed up in terms of the fact that y, height, the paddle won't change, but the x will change with the mouse. But we actually don't want it right centered on the paddle. We want it a bit to the side and just above the paddle. So let's try plus 10 and minus 10. That means 10 pixels to the right of the center of the paddle and 10 pixels above the center of the paddle. Let's see how that puts us. But then one other thing we want to do is we want to then return. Now return for a function that has a return value. So if this said int instead of void, would let us return the calculation or some end result or some property we derive. But in this case, because it's a void function, return just quits the function. It says stop going forward. It says I don't want to deal with ball movement because the ball's being held. So in this case, it's sort of a nice branching situation. If the ball's being held, just update the position based on the paddle and then quit this function. Otherwise, meaning if it was not held, then this code will be accessed because it's going to skip this if function, and instead the ball will move. So far we don't have a way to let go of the ball yet, but we should be able to press play. And sure enough, you can see there's the ball stuck to my paddle, just like we hoped. Next up, I need to connect mouse clicked event to changing is ball held to false. And we can do it kind of anywhere, but let's put that in this, we can put it in the main file. Let's do that for now, because it might find their way elsewhere. Also, I kind of like the main file system as a nice place to put file or functions that are built into processing. So like setup and draw, you see how they turn blue? It's because processing is expecting those function names. The same is true for one called mouse pressed. It might be mouse clicked. We're going to find out pretty quick. When I press play, nope, that worked fine. Alright, so you see there's a void mouse pressed. That function, because it turned blue, is one built into processing, and the moment the mouse gets clicked, that function will get called. See what just happened there? I lose the ball, and now it's my chance to click the ball, and it's going to bounce. Now also, if you look closely, watch the center of the screen, about where my mouse is right here. I'm going to click, I'm going to lose the ball, watch for it. Did you see that little green ball that briefly appeared there before it got stuck to my paddle? That's a little glitch. And if we look at what's happening here in the ball reset, it's moving it back to the center of the screen, about 70% down the screen's height. Let's just comment those out, or we could even straight up delete them. Because we don't want those anymore, we're going to let the ball held functionality be the ball reset instead. And sure enough now, that glitch is gone. As soon as we miss the ball, it goes right back to the top of our paddle, and it doesn't go anywhere until I click, which is a much more reasonable way to play because now it's up to the player's pacing after each round. They don't have to rush or know in advance where the ball is going to wind up. Once again, we can check that when we go below 0, it resets the grid, resets our lives, resets the score, and we've got a ball catch now built into our thing. And of course, with this functionality, with this Boolean value, it wouldn't be hard for us to later, for example, build a power-up that when you catch the power-up, lets you relaunch the ball. All we'd have to do is set this Boolean value to true, and the rest of the machinery would take care of itself. So that's the fourth warm-up exercise for the brick break exercises. And again, there's details I'm not covering here because that's if you didn't have me here in the video trying to explain things to you and show you how the solutions come together. Okay, now for the fifth exercise, the fifth warm-up for brick break. Keep ball from getting stuck off screen. With a new serve feature outlined in the previous exercise, it's possible to release the ball off the edge of the screen by moving the paddle up half past the boundary before clicking to serve. Because of how the ball's bounce against outer walls is handled, the ball gets stuck along the edge, zigzagging tightly up then back down. Unlike many other exercises that are about adding new features, This exercise is about addressing a pretty typical kind of bug in the code. We didn't explicitly program the unintended and undesirable behavior found. Instead, it emerged from the intersection of two or more features that otherwise work fine in most normal situations. So we saw in that previous playthrough that the game really seemed to be working fine. But the observation I want to make in this exercise is that because our paddle centers horizontally on our mouse, and our mouse can go anywhere on the screen, and the ball appears to the right of the center of the paddle, because of this combination of features, I can put my mouse next to the edge of the screen, so the ball's partway off, and when I click, it can get stuck out there, going straight up, straight back down. And in fact, I could even do it completely off the screen. And I can tell you if we sit here and wait for a moment, it's going to find its way back down, cost us a life, and reset the ball. Now what's happening is that the ball is showing up partway off the screen. And what's happening is it's further off the screen horizontally than its movement will allow it to get back on. So if we look at what happens in ball movement, if the ball is left of the screen or right of the right screen edge, if ball x is less than 0, the left side, or greater than screen width, the right side, then we're just flipping the horizontal speed. But let's say the horizontal speed is 3 and the ball is starting 5 pixels off the edge of the screen. Well, so it's going to reverse that speed, so it's going to go left 3, but then it's only 2 pixels off the edge of the screen, but it's still off the same side of the screen. So the next time it's going to flip that horizontal speed back to positive 3, and it just keeps going back and forth as it continues upwards until it's the ceiling, bounces back down, but it's not going fast enough to put itself back on the screen. There's actually a few different approaches we could take to solve this problem. One of which, you can see here I actually have outlined in the description of the details, option A, option B, and option C in the exercises. Option A is to check the ball speed when deciding whether to let the ball collide with each sidewall. What I mean by that, so any of these are actually going to be easier for us to write if we split the if condition for the left and the right sides of the wall. Here this OR bar means that if this half is true, or if this half is true, either way do the contents of the if, but that's assuming we want to handle the situation exactly the same for the left and the right sides of the screen. Let's split these up a little bit. Make a new if statement. Okay, I'm going to clear these comments out for a second just because otherwise they're going to fall out of date pretty quick with what we're writing. So if the ball's off the left side of the screen, we're going to reverse it one way. If off the right side, we're going to reverse it the other. That's just kind of our starting point. But option A says we can check the ball speed when deciding whether to let the ball collide with each sidewall. What do I mean by that is, well, okay, if it's going off the left side and the ball is going to the left, meaning its speed is negative, that's when we want to reverse it. Otherwise, it's working its way back on the screen if the second condition fails. See, whereas that OR bar meant that either one could be true, the ampersand means that both have to be true. So in this case, if we are both off the left side of the screen and we're traveling to the left, only in that case do we want to flip the ball's horizontal speed. Otherwise, we're going to leave it alone. It's finding its way back on screen potentially. Likewise, if we're off the right side of the screen and also we have a positive ball speed, meaning it's going to the right each frame when we add its speed to its position, then and only then do we want to reverse its horizontal speed. And so already we can check here that our solution A, first of all, in normal ball play, it seems just fine. Didn't break typical play. You always want to check that you didn't break the main play in addition to fixing something else. And now if I go partway off the screen and I click, you'll see the ball harmlessly found its way back on screen because as soon as it changed direction once, it did not meet the condition the next frame because the speed had been flipped as a part of our way of handling the collision. So that was option A. And that perfectly works fine. There's actually a few different ways we can do it. Option B is to incorporate the absolute or ABS function for absolute value around ball speed x to set the new ball speed to absolute value with a negative in front of ABS for crossing the right edge and no negative for crossing the left edge. So what on earth am I talking about? Check this out. Okay, I can get rid of that condition now. And instead of flipping the horizontal speed by multiplying times -1, I can set it. Okay, so think about this. If we go off the left side of the screen, we want the ball to go to the right. So if we just set the ball speed x to the absolute value of ball speed x, that's going to make it go to the right because it's going to ignore whether or not it had a negative. It definitely won't now, which is a rightward speed. And if the ball is going off the right side of the screen, then we want to make it go left, which simply means we can put a negative in front of the absolute value. And once again, whether or not ball speed x was positive or negative beforehand, we took the sign off and then we stuck one on it, it's definitely going to be negative now. In case, I know a lot of folks, when they first see absolute value in early math classes, think it's kind of insane and when would it ever be useful. Here's a situation where it actually helps to think in terms of absolute value. And once again, we confirm the ball plays as normal in normal situations. When I take the ball off the screen, it fires back on. Works just fine. Now there's a subtle difference between this and the previous one. So the previous one was actually checking an additional case every single time, but it was also, or at least in the case of the first one, if it was off the screen, it checked an additional case. Here, as long as it's off the screen, it's reassigning and recalling absolute value every single frame. At the pace of our game, with only a single ball, the difference is so negligible on a modern computer that runs in gigahertz of speed that it's not really a concern, that difference in processing. But I will say that if we had, say, 100,000 particle effects at one time that we're trying to manage and keep on screen or keep bouncing off of physical boundaries, then it would actually maybe become important to us to keep track of those subtle differences in performance. But certainly for one ball in an old-fashioned game, not a concern right now. Either one of those is perfectly fine solutions, just two ways to deal with the same problem. Now, option C is that we could jump the ball instantly to a valid screen position along the edge in addition to reversing its lateral speed. This way, no matter how far off the screen the ball is, it won't matter since it'll probably be brought back into the play area, and the next frame, its movement will be away from the wall, which is already no longer overlapping. All right, let me run that by you again. So let's look over here in the code. And what's going to happen here, I'm going to take this code back to the way it was when I first split these apart. And remember that the first way it was written was no matter which side it went off, we reversed the speed. We multiplied the horizontal velocity component by -1. So if it was going right, it's going to go left. If it's going left, it's going to go right. Now what we're saying is if it goes off the screen, well, force it back on the screen. See, so no matter how far it was off the left side, we're going to put it right at the edge, in addition to flipping the speed, which is going to mean that its next move is going to keep it back in action. We can do the same thing here. When the ball goes off the right side of the screen, notice this is there we go. Then we're going to put it back on the screen, and we're going to reverse the horizontal speed, and that's going to, once again, keep us from having a situation where the ball can stay off the screen, because no matter how far out of bounds it goes, it's going to get snapped forcefully back into place. Now there's a little functional difference here in how this edge case is going to be handled. Because it used to be that when we let go of the ball off screen, it took kind of an angle out. Here when I click, you'll see the ball went pretty vertical. And the reason for that is because within a single frame of clicking, it jumped the ball back to the middle, basically near the middle of my paddle. And as I pointed out before, in an old game like Brick Breaker, where you are in relation to the ball when you let go of it affects the angle the ball takes. So, this solution, while also equivalently, or also equally good in solving the problem, we no longer have that glitch where the ball gets stuck, has sort of an undesirable side effect, like this vertical speed isn't as nice as that angled shot in terms of involving the player or making for an exciting gameplay experience. So I would actually opt for options A or B over option C. Let's just quickly backtrack those changes to our solution B, which will be fine for us to move forward. And so if we go off the right side, we're going to go left. There we go. This is back to solution B for warm-up exercise. Now, again, you don't have to do all three of those. My point was just that there's multiple ways to solve that same problem. This kind of thing comes up all the time in game programming. So that was exercise 5 from warm-ups for the Brick Breaker example case, or Brick Break. Now, number 6 is a minor optimization in the brick countdown. Rather than recounting every brick every frame, we can instead count them only once upon resetting the bricks, or even calculate the number through multiplication as long as we're using a full brick wall at start, and then count down from the number one by one each time a brick gets cleared. So let me clarify what I'm saying here. So in our bricks code, you'll see we have an integer, global integer, because it's not inside of a class, just sitting in a file. All these files gets basically stapled together when we press compile, or the play button up here. So bricks left in game, the drawBricks function actually is recounting every brick every time. It starts at 0. Each time it finds a brick to draw, it's adding 1, plus plus being the same as plus equals 1. So it's every time it counts the bricks on the screen, it's resetting its count of the bricks. Now, for 100 bricks that we have on the screen, this is really pretty harmless, once again on a modern machine. It's actually taking us way longer computationally to draw these rectangles than to have a computer add 1 to a number. However, just as an exercise in sort of finding ways to optimize our code or thinking through what's happening under the hood instead of just taking for granted kind of the surface behavior, let's look at a way to optimize this by only, instead of recounting the bricks every single frame, we're only going to count the bricks when we reset the bricks. So here I'll set the number to 0. I'm going to borrow this line, which added to the number of bricks. And now for each brick placed, it's going to add 1. So now at the end of reset bricks, we're going to have a new fresh count of how many bricks we have. And then let's go to where a brick gets removed. Remember, this is going to be in the ball code because it's the same place we had 100 points, right? Where the location where it makes sure the ball is within the domain of where the bricks could be, calculates the position by dividing the width and height of the bricks into where the ball is to make sure what corresponding brick is where the ball should be. If there's a 1 there, it's clearing it. It's adding 100 points, which we added earlier in a earlier warm-up exercises. And here we can minus minus, which is the same as minus equals 1, or saying bricks left in game equals bricks left in game minus 1. But it's going to subtract 1 from it each time we remove a brick. And now, instead of having to recount the bricks every single frame, 30 times a second, 100 bricks, we counted it once when we reset the bricks, and we subtract 1 from it every time we destroy a brick. Now let's double check our work here, because there's some invisible stuff happening under the hood, and let me tell you, we don't want to mess this up, because that number is valuable to us, because what's happening is, if bricks left in game is equal to 0, it's going to reset the bricks. Okay? So if we somehow wind up with an off by 1 error, if we accidentally counted 1 too many bricks, if we miss a situation where bricks can be removed, this number may not reach 0 when it needs to, which would leave the player stuck in a level with no bricks and the game would not proceed. Nightmare scenario. This happens in games, certainly during development, occasionally even on release, where players can get stuck, so we want to be really sure. Let's double check this number. I'm just going to print this number out to the screen, the same number we're using elsewhere. I'm going to print it in the middle of the screen, because it's kind of a handy spot, so half of the width of the screen. We'll also put it 15 down. Also, these numbers we've been printing, they've been green. I'm going to go and change our fill color here to, they were green because our ball uses, let's see if we look at the draw ball code. See, drawing the ball, filled our color with green, 0 red, full green, 255 out of 255, 0 blue. RGB, full green, we had a green ball. Fill keeps that color persistent until the next fill call happens, which in this case would be the dark blue for the background. Let's also make this text white while we're at it. Oops. Full red, full green, full blue. Now it's going to be easier to see all 3 of our text lines, including this temporary one. We're just going to put out what's really debugging information. And you'll see we have 100 bricks, 98, or 99, 98, 97, 96. That number seems to be counting down. We might miss the ball. 95. It doesn't reset when the round resets, which is good. But we also want to make sure that, like, when we lose the last brick, it's going to clear them all. And, like, you know, this takes a long time to do. We don't want to have to, every time we make a change to the features, have to play through our game to make sure we can double check everything. We might mess up, we might get bored, we might run out of lives, and then we have to reset our progress, which, by the way, we can test that immediately. Lost the ball, 100 bricks again. So far, so good. But we'd like a faster way to clear the bricks in a very authentic way. What I mean by authentic is, if we just wrote a function to erase all the bricks, I am not quite confident that that would be exactly the same as the ball destroying the bricks. So what we can do is, here at the top of ball movement code, I'm going to say if mouse pressed, ball x equals mouse x, ball y equals mouse y. And these are red values because they are built into processing. Mouse pressed is a true or false of whether or not the mouse is down. Now don't confuse this with our void mouse pressed. This function gets called one time the moment the mouse goes down, whereas this variable is true every frame the mouse is held down. Either button. See? The difference being that this happens once, which is like we want to release the ball in an event, or like a jump button in a game. This is something we can hold down, like an auto fire or like a sprint button. And when the mouse button's held down, we're going to override the ball's normal movement, set the position of the ball to the mouse's current position, mouse X and mouse Y are integers, always up to date on the current location of the ball, and then return, just like we bailed on the function for ball held, we're going to bail when we're holding down the mouse. So I'm going to press play, and now I can click and hold it, and I can just drag the ball through the bricks. This is a whole lot easier for testing. You can see we can test the score. I can put the ball somewhere I can let it go for a second, let it do some damage. And what we can verify is I can kind of use this as a paintbrush to erase these bricks. I'm just holding down the mouse button, dragging the mouse around. We have 4 bricks left. That seems to resemble the amount that we have still on screen. We have 1 left. I'm going to let this one get destroyed organically. Okay, 0 bricks. So when I hit the next ball with my paddle, back to 100 bricks. Perfect. That's great. So you were able to test that. In the meanwhile, let's comment that out. /* is a multi-line comment that ends at */. This will go back to ignoring it, but having this kind of functionality handy in the program is good for verifying features like this. Likewise, don't forget that that brick count is also something we don't really need to display to the player. But we might just comment it out for now because it's going to be very likely we're going to want to easily debug a visualized number on the screen again, and we just put it right back there where we had this one. Okay, so we've done that minor optimization to the brick countdown. Again, for performance reasons, this is totally unnecessary for a game of this complexity. But if we had thousands of balls in action, this kind of thing actually wouldn't hurt. It wouldn't have any effect because we're counting bricks. Basically, these kind of optimizations are useful to have consideration over, know something about, and it's just an exercise. It's a warm-up. Okay, 217 images for bricks, paddle, ball, and background. Everything in the game is currently drawn with rect and ellipse, shapes made in code. Instead, create some image files and use those in place of the programmed graphics. Okay, well, tell you what, the way we would make an image in processing is we create a new folder called data. And data is where your assets go in processing. It's where you can put your image files, it's where you can put your sound effect files or your music files or so on to then be referenced in the code. And again, this directory is the same place we've saved our source, which is documents, processing, and then within the CodePak bundle, I'm just overwriting the stuff that was unzipped from the sample. We could always go back to the original zip file if we needed it. Now, if we want to add those files, we could go through and draw them. I could open up Photoshop. I have, of course, drawn them in advance to try to save us some time and trouble. This is not really fundamentally a training experience in making the images, but it's worth the practice if you've never done it before to use. If you have Photoshop, that's great. If not, the tool at GIMP.org is a fairly reasonable free alternative. There's a lot of other options out there to Google for, but you want to make sure it's an image program that ideally supports layers, which is helpful for things like transparency or pieces of images that you can then move separately from one another, and transparent image formats like PNG, which is good for having a section around the ball, so as opposed to having, like, say, a white square and you can see the corners around it, having just the circle of that image get drawn. It's all about using transparency in your images, which is going to require saving as a PNG format. So we want to have images for the bricks, paddle, ball, and background. Let me get these pictures I have in advance. Bricks, paddle, ball, and background. Paste those into my data folder. Let me show you the images I'm working with. I got this tiny ball I made, a little 12 by 12 pixel. It's based on roughly the size of the ball we're working with in the game. My background image, I just threw together obviously some cheap Photoshop filters quickly. That resolution is 640 by 480. It's helpful by having the background image the same resolution as my game's window. I can just redraw this each time instead of that blue rectangle to wipe the screen. My bricks, I've made it 59 by 19. Now, why did I do that? Well, if we look into the bricks definitions, we'll see that the brick's width is 60 and the height is 20, but that we have a gap of 1 that we're expecting to draw. So that's why I've stuck to 59 by 19, 1 pixel less than 60 by 20, so that these bricks will be consistent in size with the bricks that we drew in game. Then lastly, the paddle, I made it 60 by 10, because again, if you look into the paddle function, we've set in code the width is 60, the height is 10, and at the end of the day, it really saves us a lot of trouble if our assets line up nicely with the dimensions that we're using in code. So I've got each of those graphics now, but we need to load them into the game. In order to load them into the game, each one needs a p-image reference. And p-image is going to be our reference or our handle on the file in memory after we load it from the file. And so let's name those ball, BG, ball, background, brick, paddle. And actually, it's kind of handy to, there we go. I'm going to start each one with the IMG and then camel case the first letter. That way, when I see these variables floating around, I'll know exactly what I'm dealing with. I'll know these are the images. That's the IMG. As opposed to, like, is it a Boolean on-off? Is it an integer? Is it a counter for bricks? What is it? I'll know that IMG brick is a handle on the image for the brick. Now in void setup is where we can load the images for these different variables. And we do it in setup because we only have to load the images once. We do not want to load the images from disk constantly while the program's running. It's kind of sloppy and unnecessary. And what we do is, so we say load image, and here in the parentheses I put, or in the quotation marks, the name of the file I want to load. So like ball.png. By the way, if when you look at files on your system you don't see extensions like .pd and .png or .jpg, it's well worth taking a moment. Google for how to turn off hidden file extensions on your system. If you're on Mac, if you're on Windows, there's different ways to do it depending on the version of Windows. It's often in folder options. But basically, by default, operating systems want to hide their extensions on their files. As a programmer, you really want to see those. It's going to help you out to know what format an image is in. It's going to help you out to know which file is your program, which is your source, to rename it, as well as to reference it in code. You're going to need to know that extension. So if you don't see the extensions on files, take a moment to get that figured out. Come right back. Likewise for load image. Now I want to point out too that part of what's nice about these, I use the JPG for the background because it doesn't need transparency, it's just a big rectangle, is that as long as they're in the data folder in processing, we don't have to indicate the relative path because it's assuming to check in the data folder for this sketch. Brick. Now you'll see here there's a chance where I could have made a typo by copy and pasting. This could have looked for brick JPG. That would give us a null pointer error in our program because it's supposed to be PNG. That's again why extensions matter. I'm going to do one for the paddle as well. Yep, that's just called paddle. And now we could have loaded these images each within our separate files. We could have put the P images in separate files. Totally a matter of personal organization. I actually kind of like pooling together all my images, assets, and audio kind of in one place in my main file. It just kind of helps keep me clear about what's loaded in my program, especially for an example like this size. We're probably going to load the assets all at once when the program starts, and leave them there the whole time. No need to spread all that stuff around. So we now have a reference to each one, and we now have to display them. Let's do the background first. It's going to be the easiest to do. So here for draw, we had a fill and a rect. And that fill set the color to navy. That means little red, little green. It's kind of small amount of blue, so dark navy. And then a rect, which is the same dimensions as the screen. Now by commenting this out, I'm going to show how important it was that we did that, because without it, we get this kind of crazy sort of drawing program thing where stuff doesn't get erased. See, because what's happening is the previous frame isn't ever being drawn over, and it's just leaving this smudge on everything, which is kind of artsy, kind of interesting, and super hard to play. What we want to do instead was either blank out the screen with a whole big old body of navy blue, or image background 0, 0. This says to take the image that we've loaded from the file, using load image up here, into that handle, image background, display that image reference. 0, 0 then is the top left corner in X and Y coordinates for that image. And so already, you can see there's our background image. We've fixed the smudge problem because every single time this game gets drawn, the first thing it's doing is it's slapping that picture over whatever was drawn in the previous frame, so it creates a better illusion of movement and doesn't leave any trail. Okay, I'm going to delete those things we commented out. So background's accounted for. Let's draw the bricks next. So let's draw the paddle next. All right, so let's go over to the paddle drawn. Now if you look here at this rect call, it's drawing the x position not at paddle x, but at paddle x minus width divided by 2. So the coordinate we keep track of for the paddle is actually, in this case, the vertical center and the horizontal center of our paddle. Because one thing which we could do by accident, see, if we said image paddle, paddle x, paddle y. Oops, all capitals because it's constant. Okay, if we did that again, this is the top left corner of the image placement, not the center of it. And so when I press play, I'm going to draw both at the same time. You'll see how they don't line up. And most importantly about not lining up, the yellow paddle that you still see there is the one that the physics that we've written for the game's ball to paddle collision is using. So we'd be really in trouble if we erased the rectangle and then we'd only see the image for the paddle in the wrong place. This could be a real problem because it means that we'll go right through the right side of the paddle and left of our paddle will reflect the ball. So what we really need to do, and again we're going to draw both at the same time to highlight that offset, see how they don't line up. So rect, the first two arguments of a rect are the x and y coordinate of the rectangle, the third and fourth of the width and height of it. And that's what we want for placing our image, the left x and the top y. So I'm just going to copy and paste that xy from the paddle, from the rect version that we previously had. Now when I press play, you'll see that it completely is overlapped by that yellow paddle. And sure enough, when I erase the rect that was drawing the paddle, and we no longer need this yellow. In fact, let's set that to full 255s, so it'll give us sort of a proper white fill if we use any other drawing elsewhere. There, you can see there's our new paddle. And it's reliably placed based on the coordinates that our physics use to determine how far it is from the center. That ball is getting hard to see. Let's go ahead and fix that up. Now draw ball is going to be a little bit different. And here's why. Ellipse by default, as explained in the warm-ups details, ellipse, x and y values for ellipse aren't the top left corner like they are for a rectangle. Instead, that's the center coordinate, and then 10 becomes like the width and the height of the shape. So here we'd actually have the same problem. If we set image, img ball, ball x, ball y, and I'll show you how, again, we're going to leave image and ellipse temporarily both working, so you can see once again how they'll help us see where the error is. If you look closely, you'll see that there's a ball graphic being drawn down and to the right of the green ball. But again, that green ball's center point is being used as the top left corner of that ball graphic. In order to fix that, we have to actually account for half the ball's width and half the ball's height. Do you see that? Or there's actually kind of a nicer way we can do that. Here I'm just sort of assuming 5, but like we said earlier, the ball's image is actually 12 pixels wide, not 10. We can make sure we don't have any mismatch between our data and our visualized offsets by using the width and the height variables on the image data that we loaded. This is the sort of thing you can learn from looking at processing.org's reference materials. But this way, it's going to stay centered no matter what dimensions we make that ball. Now currently, because of the way our game's physics is written, it's acting just as a point in space, the center coordinate of the ball, so it's really just decorative, drawing a bigger ball, or making it easier to see. But now you can see how tightly overlapping that green ball is from the other one, to the point that it basically is barely visible as an outline, and 1 pixel outline around that green ball. And when I erase that ellipse call, all that's left behind is this ball graphic. So there we go. And last, let's fix those bricks. I think that's going to make a big, nice difference for us because, of course, there's so many of them. Now, the first point I want to make about the bricks, as some programmers will already know, but I want to make sure we're all on the same page here, is that you only need to load the brick image once. We don't need a bunch of different copies of the image. We don't need to load a bunch of them into memory. We need exactly and only one image brick, because then we're basically going to stamp it out for each brick we're drawing, that same reference in memory to that same one image that we loaded. We'll look at where we draw the bricks, and then see there's a rect call for drawing each location in the grid that corresponds to where there's a brick. And you'll see that once again there's a computed x and y for where the brick should go that the rect was using. Well, we're just going to straight copy that as our x and y values for the brick. Now you may have noticed too, by the way, that I occasionally take some liberties about when I skip a line after a comma. In case you're not already familiar with this, white space in programming is totally up to you in a lot of programming languages. Whether you're in C, ActionScript 3, in this case Java, which is sort of the core of processing, you can skip a line, you can put a space wherever you need it in many cases. The formatting is just a matter of keeping organized. Same thing with the indentation, but it really helps to stay good on indentation. So here we're going to draw the image of the brick at the same computed coordinate as we drew the rectangle. Now let's take a moment to break down how this computed coordinate works. Let's not just take it for granted. We have a top left x and y. That's the offset from the corner of the screen of the x and y. And then we have plus the column of the brick we're currently looking at times the brick's width. So if the brick is 60 pixels wide and we're looking at the, say, second column in, we want to skip 120 pixels to draw that brick 120 pixels in for that next column of bricks. Same thing for row. It's going to multiply times the height. So if we're looking at, say, 4 bricks down, this will take the height of the brick, 20, and it'll draw it 80 pixels down for the top. But, more importantly, it works. There's our bricks, here's our paddle, And again, the coding wasn't that involved to put those images in there. Now, these are just sort of some images I threw together for sake of illustration. I appreciate these aren't great pictures. This is sort of just getting it done in Photoshop. But of course, what's cool about this is that no matter how good you make the images, if you 3D render some stuff, if you really pour your time and energy into making some awesome backgrounds, the exact same code is going to work for it. It's the exact same code no matter whether the images are crummy or whether they're great. So you can put as much time as you like into the art layer to really help this game shine. In any case, we can probably almost certainly agree that for as crummy as it still looks more polished and more complete than it did when it was just some colored rectangles, right? We even have some clues in there, like this darkness at the bottom helps imply that that's the sort of the gutter that the ball falls into. So that's the end of warm-up exercise step 7. Now you can see there's my example. I kind of showed the kind of images I used. Now let's look at icons for lives. Now, instead of displaying a textual number for how many lives a player has before the game resets, many games prefer to instead show a series of icons to display the remaining tries in a more visually appealing manner. Figure out an icon you'd like to use, like a heart, a ball, a star, or a tiny paddle. Create that image, and in place of the lives text, display instead show a horizontal row of that image stamped out once for each remaining try available to the player. Okay, so once again, I've already made an image in advance for this. I just took the ball that we already had and I painted it yellow. Just sort of like ran a screen or multiply filter or whatever. So we now have like a gold ball. So we can have a stack of gold balls in the corner that shows how many lives we have remaining. We have that PNG in my data folder. I'm going to have to, first of all, create a new P image. We can put this on its own line, doesn't really matter. Image life. You'll notice too that I'm not calling it gold ball in the code because I might change my mind later and want to use a heart for lives. I don't want my code to have to mismatch and keep up with what the names are of my files, so I name my images functionally rather than descriptively of how the abstraction is done. And this was called life.png. Okay, we now have a handle in memory on the file that we loaded from the disk space in setup, and now we can draw that anywhere we want. And what we're going to do is here, where we were displaying text for the number of lives, we're instead going to do a for loop. I is going to start at 0. We're going to count up as long as I is less than lives. I++, pretty typical for loop. If you've never seen this before in programming, you should probably go back and view some of those other videos I got. I think you're going to appreciate learning some of these basics. And then we're going to present image with the image life for a position, let's say 50 pixels from the side of the screen. That will give us wiggle room for having multiple lives. And let's say I times the width of image life plus 2. And the vertical position 15 from the top. Now, this might look kind of like witchcraft. What in the world's going on? Okay, well, for starters, our baseline. So on the 0th life we have left, in fact, when we have 1 life left, it's going to display at 50 pixels from the side of the screen as its left coordinate. Again, so we have room if we have multiple lives. Then I want to multiply times the number of the life we're showing. So for the 0th life, 0 times any number 0, it'll show exactly 50 pixels from the right side of the screen as its left edge. For the next one, this is 1. It's going to skip over the width of one image plus 2 pixels for some space between them. And then same thing for the second one, it's going to skip over another interval. What it's going to do for us is that now our lives display, looks like we're a little low, kind of overlapping the bricks. I'm going to change that 15 to 5, so maybe we'll get some more elbow room. That looks much better. Now you see up here, it's skipped 0 widths, 1 width, 2 width to draw the third life. And sure enough, when I lose a life, the counter goes down in the icons. See, I can lose another one, Now I'm down to 0 lives left. When I lose it, bricks reset, score resets, lives reset. And again, what's neat about all this is that because we've already written the fundamental code to behave as it should, even though we changed the display layer of it, it all still functioned the same way. We only had to go in and muck with replacing that number with something to display icons for the number of lives we have remaining. Okay, now at step 9, I believe this is the last warm-up exercise. Let me double check. Yeah, okay, it's our last warm-up exercise. We're going to add a title screen. Instead of starting immediately when the program is started or reset, the game should instead pause briefly on a title screen. Create an image in your image editing program of choice, or construct one programmatically with shape and text code, and have that screen displayed to the player until the mouse is clicked to start the game. Remember to include on the title screen a clear message indicating the player must click to start. Return to this screen when the player runs out of lives. Display someplace on the screen the player's score from the finished round, since the player may be too distracted trying to catch the ball to notice the score moments before losing. Okay, once again, it's going to take a new image. Now what I did for my title screen, because I knew it needed to be the same basic dimensions as the background, I just opened up my background image, did a quick little recoloring of it, threw some text on it. I used Photoshop, you can use GIMP or other tools, and I said Brick Breaker, a hobby game dev demo. But again, most importantly, I said click to play. If your game needs spacebar press to start, or enter key, or a mouse click, you gotta tell the player that, but they're gonna sit there thinking maybe your game's loaded, they'll get frustrated. Don't make it their problem to figure out how to start your program. So I've got that JPEG there. Once again, a JPEG works because I don't need any transparency. I'm going to want a new pimage handle on it, so image title screen. I'm going to load that image. Now technically, we don't need these other images when we're on the title screen, and we don't need the title screen image when we're on the other screens. If we wanted to try to take this code to another level, if we had a lot of things going on in our program and we just needed every ounce of memory we could squeeze, we could theoretically only load that image for the title screen, then when the gameplay starts, dump the image and load these and have fewer images total in memory. In practice, for a game of this size, that's totally unnecessary as a level of overhead on your programming. Do what's simplest, do what gets it done, optimize later. Premature optimization is something all programmers have to be careful to not get caught up in. So we have this image, we have a handle on it, we've loaded it. We have to decide when to display it. So just like ball held is a Boolean value that we can set to true or false, let's have one for on the title screen. Boolean is on title. Okay. And inside of setup, let's default that to true, equals true. We know that when we're on the title screen, we want to display that instead of the game action. So if we're on the title screen and draw, I'm just going to copy this image background call. The only difference being we're going to have image title screen. Okay, and we're going to bail out of this function, return, just like we did when we were handling the ball motion. This will let us skip out of the rest of the draw. So if we're on the title screen, it's only going to display the title screen and then quit draw before it happens for the rest of the function. Again, even though it's been called 30 times a second, when we're on the title screen, all we want to do is just reinforce that image. We don't have to redraw it, but it's harmless to. We'll just do it here for simplicity. Now, the other thing we want to do is bail out of the title screen when you click. Well, clicking also lets go of the ball, which maybe isn't what we want, because that means that the ball would be starting moving as soon as we clicked past the title screen, unless, if we're on the title screen, then set title screen to false. Else, let go of the ball. This is a pretty common, good case for using an if and else. See, if we click the mouse and we're currently on the title screen, bail us out of the title. Otherwise, meaning we weren't on the title screen, we must be in the gameplay, try to let go of the ball. And if we already let go of the ball, then it's harmless to reassign this to false. And lastly, we want to put the player back to the title screen, actually almost lastly, when they run out of lives. So, ball's reset, is on title true. That's going to eject us back to the title screen because the next time the draw code happens, it's going to ignore the gameplay. We're going to be on the title screen. As mentioned though, because our score doesn't display on the title screen and it gets reset before it gets sent back, we do want a good way to show the player what their score was when they were playing. And this is a little bit more roundabout, but I'll show you how I'm going to hook this up in kind of a lazy way. Int prev score equals 0. Okay? So the previous score, 0, by default. When we display the screen, right after our title screen, if prev score is not equal to 0, then we're going to display the text for it. Let's say 15, then a little bit above the bottom of the screen. That seems fine to me. Let's also add a fill to make sure our fill color is a bright white for the text. Okay, bright white color for the text. Fill, remember, affects all the lines after it until a new fill color gets set. Full RGB for white. That's going to display our previous score on the title screen if we have one. And the way we're going to know if we have one is here in the game reset, right before we zeroed out the score because we ran out of lives, we're going to set that equal to score. Simple. It's an extra variable, but it's harmless and it's an easy enough way to handle this. So score will display somewhere down here. It's actually, see this white bar at the bottom? I'm going to bump that score up a little bit higher for the score display. Otherwise, I'm afraid we might actually see our text get hidden in that white bar since it's white text. All right, click to play. Okay, I'm going to get some easy points here. Not really worried about my score. See what happens on a round of lives. 400 points, and there's my 400 points down here. Could be displayed more gracefully. We could say something nice. Looks like we maybe went up higher than we needed. We could combine the string and say like previous score plus, and this lets me combine a string using the plus sign. So we'll have the text previous score with a space, previous score with a space. The plus sign then is going to concatenate on this number to the end of it. So there's no confusion to anyone playing this of what that number means. Oh, let's see, get some points, 300, 400. Remember, this isn't saving between rounds or anything. We could do that for another example elsewhere. We do in another game. But previous score, 800. There we go. And if we play it again, we want to confirm that we no longer see the 800. Let me get a shorter score. Uh-oh. This is quickly gonna, I can't play any worse than this. 700, 800. Okay, now we're going to exceed 800. We just want to confirm we can get a range of scores on the title screen. It's always good to test a feature. Even if it seems like a simple one, it's good to test. There's our 1,000 points we had. Now again, this time I'm just going to play it safe. I want to get a minimum score. Each time it's going to bounce off one brick. Oh, I messed up. Okay, 500. Great. Okay, we've confirmed it. And again, when I run the game, it's not saving the scores or anything. It's only within the gameplay session that it keeps track of the previous score, since otherwise you might miss it while you're playing the game. So that's all the warm-up exercises for the code pack. There are additionally practice exercises and challenge exercises. Quickly go over what those are for this particular game and the sample code. Practice exercises including more points for hit chains, ball speed increase, extra lives for score milestones, and power-up functionality, the fireball. Challenge exercises include bricks loaded from a 2D array in code, so you can have like different shapes of levels, different brick types, like gold bricks that take multiple hits, or silver bricks, or invincible bricks, implementing modern brick collision, as opposed to, in the next one, trying classic ball brick collision. That has to do with a ball that either behaves in a more predictable, modern manner, or one which uses the old-fashioned, pretty weird rules, which are described here in the exercises, followed by loading a level from a file, so you can have text files to design your levels, organizing your code into classes instead of just separate files, having multiple types of power-ups, a cannon, a multi-ball, sticky ball, and points power-ups, and then having a series of levels which you then design using your level-based outside text files to create a series of levels that use the different bricks and different power-ups in interesting and worthwhile ways. So that's just the exercises for Brick Break, which is what's included in the sample. Again, if you're interested in the general code pack, the full bundle of 1 and 2, there's 6 games total in there. Okay, thank you so much. This is Chris Leon for Hobby Game Dev, and I'll hopefully have some more videos for you soon. Thanks. Bye-bye.